When Elon Musk stood on stage at Tesla's Battery Day and made the claim that there were already batteries in limited production that could exceed 400 watt-hours per kilogram, most of the industry treated it as typical Musk showmanship. Analysts rolled their eyes, journalists labeled it as yet another example of Tesla hype, and critics dismissed it as unrealistic science fiction. But, as has happened many times before, words that initially seemed like exaggeration have quietly evolved into a kind of roadmap. 5 years later, that roadmap is starting to take physical shape, and the possibility of a Tesla-built electric aircraft is becoming harder to ignore. This isn't about wild promises. It's about how small, incremental advances in battery chemistry, materials science, aerodynamics, and propulsion can converge into something transformative. The concept of a Tesla super-electric plane aiming for a 400-mile range and turnaround times as short as 12 minutes isn't fantasy anymore. It's plausible engineering that could redefine aviation. What makes the idea compelling isn't just the batteries themselves, but the way every design choice stacks to create a system that squeezes every mile out of every watt-hour. Day after day, this aircraft would need to perform with the same consistency as conventional planes, but with cleaner operation, less noise, and lower operating costs. To get there, Tesla is leveraging some of the same strategies that helped to dominate electric cars, reducing drag through smarter materials, optimizing propulsion systems for efficiency and redundancy, and rethinking how energy storage and cooling are integrated into platform. One of the first elements that give this plane its edge is the exterior. Conventional aircraft fuselages are made from multiple aluminum sheets joined by rivets, leaving countless seams and surface imperfections. The Tesla super electric plane would take a different approach, using a single-piece composite skin that drastically reduces the number of joints. This one-piece construction makes the surface flatter and smoother, and when it's treated with a hydrophobic nano-coating, even environmental buildup like dust and rainwater struggles to stick. In aviation, this matters a lot. On small and mid-sized aircraft, skin friction drag can account for nearly half of the parasite drag that eats away at efficiency. Even a small percentage drop in that coefficient translates directly into range. With composites and nano-coating, a drag reduction of 2 to 5% is within reach. That doesn't sound like much, but when you remember that cruise power demand scales directly with drag, those small improvements become extra miles in the air without needing heavier batteries. The wings continue the same philosophy. They're long, slender, and equipped with winglets, pushing the aspect ratio higher than usual. Aerodynamics is about balancing lift and drag, and one of the key ways to reduce induced drag is to stretch the wingspan and reduce wingtip vortices. By raising the aspect ratio from something like 10 to 14, induced drag can be cut by nearly a third. Adding winglets acts as if you've tacked on even more span without the structural penalties, offering another 5 to 10% improvement. On top of that, the landing gear is tucked away into sealed bays with flush doors, eliminating another source of parasite drag. On aircraft where the gear remains partially exposed, wheels and struts can add several more percentage points to drag and cruise. The cumulative effect of all these features, slender wings, winglets, sealed gear, adds up to noticeable energy savings at real-world operating speeds. For an electric aircraft, every single percentage point matters because you can't fall back on a giant fuel reserve. Even the details that seem minor at first glance, like inlet design and maintenance panel placement, become critical. Tesla's concept relies on smooth, flush-mounted inlets positioned in favorable pressure zones, with carefully rounded lips that let air flow in with minimal separation. The ducts behind them are short, keeping pressure losses down. Protruding antennas, bolts, or panels are minimized and sealed flush with the fuselage. It may sound trivial, but in practice, each of these small bricks in the wind adds up to measurable drag. Reducing their total surface area can shave another 1 to 3% off drag and cruise. With traditional jets that run on kerosene, that's a nice-to-have. For a battery-powered plane, it's essential because that margin translates directly into extra minutes of flight time and extra miles of range. If you imagine yourself as a chief engineer, you'd be asked to decide where to put your design emphasis. Would you prioritize a nano-coated one-piece composite skin, wings with high aspect ratios and winglets, or the ultra-clean flush paneling and inlets? Each choice unlocks extra range, and the beauty of Tesla's approach is that they don't have to choose just one. They can stack them, compounding efficiency gains to create an aircraft that performs at a level skeptics thought impossible. But aerodynamics is only half the battle. The propulsion system plays an equally important role, and here Tesla leans on distributed electric propulsion. Instead of relying on just two large engines, multiple small motors are embedded along the wings, each paired with a variable pitch propeller. This arrangement spreads thrust evenly across the wing, smoothing airflow and allowing for smaller wings while still meeting lift requirements at low speeds. That's important for takeoff and landing, where safety margins matter most. By blowing air over the leading edge, the system allows slower, more controlled approaches and departures, which reduces noise and improves efficiency. During cruise, distributed propulsion also helps reduce drag. A smaller wing has less wetted area, meaning less parasite drag overall. In practice, this design tweak alone can save 3 to 6% in cruise power demand. The variable pitch propellers add another layer of optimization. Every motor and propeller combination has an efficiency sweet spot, but flight conditions are constantly changing with altitude, speed, and load. With pitch control, each propeller can be kept closer to that sweet spot, nudging overall system efficiency up by 1 to 3 percentage points. When you combine an inverter at around 98% efficiency, a motor at 95%, and a propeller in the high 80s, the chain comes out to somewhere between 74 and 83%. That's already good, but distributed thrust and pitch control push it even higher, shaving down the kilowatt hours needed per nautical mile. Maintenance and reliability also improve with this architecture. The electric motors deliver high torque at low speeds, which means they can drive the propellers directly without a gearbox. In conventional aircraft, gearboxes add mechanical losses of 2 to 5% and require expensive overhauls after 1,000 hours. Cutting them out entirely raises efficiency and slashes recurring maintenance costs. The motors can also provide regenerative braking. On descent, the propellers can windmill under controlled conditions, feeding a small amount of energy back into the batteries. It's not huge, maybe 1 to 3% of the flight's total energy, but it's enough to power auxiliary systems and slightly reduce net battery drain during approach and landing. Plus, the drag created during regeneration takes strain off the mechanical brakes, meaning brake pads, wheels, and landing gear.